All right, here we are for the second part of section 5.9, 5-9, complex numbers. This will be a much shorter video. If you missed that last video or all of it or didn't understand part of it, please go back and watch it. It's one of the most complicated concepts. It's a brand new idea. It's one of the most complicated things we talk about really all year. So now we're going to go ahead and apply it a little bit more to a couple other kinds of problems. Last time we took a look at expressions and solved expressions and so forth, simplified. One of the things I'm going to put at the top here again today is that the square root of -1 is I, and -1 is equal to I squared, or I squared. Let's turn that around. I squared is equal to a -1. Usually we see I squared and we have to turn it into a -1. And if we see a square root of -1, we turn it into I. It's usually going in this direction. So let's just take a look at some more of the problems from your homework for today. A little different type of problems, but you shouldn't have too much trouble with these. Let's take a look at number 12. This is on page 274. Number 12, it asks us to actually solve the equation. Now, in the past, we've had trouble solving this because we didn't have a way of solving square roots of negatives. So let's take a look at number 12. It asks us to solve this. Now remember, anytime you have a problem with a square in it, you're going to have two answers. So you're going to have a plus or minus answer here. We'll go through that and show you how that works again. All right, how do you get x alone? Well, it's been squared, multiplied by 2, and then 18 was added. So we're going to undo it by working backwards. Let's start by subtracting 18 from both sides. And now let's divide both sides by 2, and we got x squared is equal to a -9. Now in the past we saw this and we thought, well, that's not possible, and we would write no solution here. But now with the introduction of imaginary complex numbers, we're going to take the square root of both sides. Now remember, whenever you take the square root of both sides to solve for x, the square and the square root undo each other over here, but on this side, you end up with plus or minus the square root of -9. So we're going to have two answers here. Now, I'm going to break this apart because, in the future, you're not going to need to do this. I'm going to break this apart into two perfect squares. 9 is a perfect square, and -1 is a perfect square. Remember, -1 is a perfect square. It doesn't appear to be at first, but it is. So our answer is plus or minus the square root of 9 is 3, and the square root of -1 is I. So there's our answer. X is plus or minus 3i. Notice we usually put the I at the end, put it like a coefficient in front. I is not a variable. I is just an indicator that it's the square root of a -1. Let's look at the next one. All right, let's take a look at 13. Same basic problem as we had last time. Let's subtract 32 from both sides. And let's divide both sides by 4 here. And we get x squared is equal to a -8. Okay, now we're going to take the square root of both sides. And when we do that, we end up with x here, but on the right, we end up with plus or minus the square root of -8. Well, let's break this -8 up into perfect square factors and then the ones that aren't. This is plus or minus the square root of -1 and 4 and 2. Remember, -1's a perfect square. Today I'm going to just circle the ones that are not coming out. Okay, so this one's not coming out. In the past I've circled the other ones. So this is the square root of 4 is 2 and the square root of -1 is I. So this is plus or minus 2i root 2. 2i root 2. Square root of 4 is 2. Square root of -1 is I. So we could write it this way, or you could write it separately. 2i root 2 and -2i root 2. I'm not sure how your book does it, but both answers can be written separately, or you can just combine them together. Well, there it is. It's the same process. Let's do another one, number 14. All right, let's solve this one the same way. By the way, you'll notice all three of the problems we've done here have had an A x squared term, and they've had a c term, but there's been no b term. This process we're using the square root property is only usable when you don't have a b term in the middle, like bx or something like that. All right, let's add 25 to both sides. And divide both sides by a -5. And x squared is now equal to a -5. And again, take the square root of both sides. We'll get two answers, plus or minus. Well, I don't need to write it out here, but the square root of a -1 is I, and the square root of 5 stays behind. So, I mean, you could write that out if you wanted to, -1 times 5. Square root of -1 is a perfect square, see, right up there, okay? All right, let's take a look at a slightly different problem here. We have to kind of get our mind around something a little different here. All right, let's take a look at problem 15. Now, the instructions on problem 15 said find the value of m and n. And this has actually got two things in here that are unknown. I, of course, is not a variable, right? But m and n are unknown. And somebody might be tempted to say, well, do I have to solve the system? Well, not really here, because m and n happen to be parts of different set groups. For example, if you look at m here, there's no I over here. So this is real. But here's an I. This whole thing is multiplied times I. So this part is imaginary. So it's a real part plus an imaginary part. And over here, this is a real part. And this part here is imaginary. See, we've got the real plus an imaginary and real plus imaginary. So really, we're just going to set the real parts equal to each other. So 2m equals 6 and solve that. And then the imaginary part, 3n plus 1 equals -8. Now you notice I didn't even bring the I along because this is the coefficient of the imaginary part. Just the coefficient. The coefficient of the imaginary part here and the coefficient there. So you don't really need to bring the I along. If you did, you could just divide both sides by I eventually. But we don't need it. It's the imaginary coefficient. Okay? So let's solve each one. Here it's easy to see that m is 3. And over here, let's subtract 1 from both sides. 3n is equal to a -9, or n is equal to a -3. So the only thing you need to notice on this problem is be able to recognize the real parts and the imaginary parts as you're doing those. I'm going to let you do number 16 on your own. And then we're going to tackle problem 17 together. Let's take a look at it. All right, let's take a look at problem 17 on page 274. You're going to need to get your book open so you can look back at it. I've got it up here right now, but in a minute I'm going to take this down so you'll need to kind of follow along in your book. As I mentioned before, imaginary numbers have applications in life, and one of those applications is electricity. I'm going to show you in a minute the theory behind that and why that's so. But this part is asking for the current in one part of the series is 4 minus 7 amps, excuse me, 4 minus j amps, and the current in the other part of a circuit is 6 plus 4 j amps. Add these complex numbers to find the total current in the circuit. Now you'll notice the question, add these complex numbers. What it's telling us is that these are both complex numbers. And if you're like most people, you ask yourself the question, where is I? Isn't I part of the complex numbers? Where did this j come from? Well, electricians, electrical engineers, don't use I here because variables and letters can get confused. I has a different meaning in electricity. So to avoid the confusion, the electricians use J instead. So when you see a problem that looks like this with a J in it, that's a complex number, and the J is the imaginary part. J is imaginary. So just think of this J as I and just treat it the same way you would an I. Remember, J squared is going to now be -1. The square root of -1 is J. So they mean the same thing. Just bear that in mind. Now it says the current in one part is this and the current in another part is that. Find the total. Well, what do you do to find a total? You add the two of them together. So let's go add those together, and then I'm going to come back and explain the application here. All right, so here's the laid out equation of problem 17. It talks about the amps being these two different amounts. I'll put parentheses around them so you can see the two amounts. In one part of a circuit is this, another part of a circuit is that. And it asks for the total. Well, this is like one of the first problems I did for you. Simply add these two together. You see the real parts and the imaginary parts? Well, the real part would be here and here. And the imaginary part is here and here. So we're just going to add those together. 4 plus 6 is 10. Negative 1j and positive 4j is a positive 3j. So that's your answer. You're just finding the total, and this is in amps. Let's take a minute to talk about why we're using imaginary numbers in electricity. By the way, amps, you probably heard the term of amps, and you probably heard the term of volts. You probably heard things like current and resistance, things like that. These are all electrical terms, and if you need to solve something, they're going to give you the particular formula for those electrical things. So anytime you see an electrical problem, you're going to recognize, oh, these are J, those are the imaginary parts. Now let's talk about why this is being done in electricity. Okay, why do we need negative square roots? All right, now why do we need negative square roots in dealing with electricity? Well, if you know anything about electricity travels in circles. Let's start with what's called DC electricity. And here's a battery. It could be any kind of battery. It could be a car battery. And here's a light bulb. And the light bulb is shiny here. DC current in electricity usually flows in one direction. Now, some may have difference of opinion on how it flows, but it flows out of one terminal, goes into your light, and then it flows out of the light and it comes back to the battery. That's why it's called a circuit. It's called a circuit because it makes a circle. If you have a break in the circuit somewhere, let's say you got a switch in here. We'll put a little switch in the middle here. If you got a switch in here and you flip that switch, you're breaking the circuit so the electricity doesn't flow. Electricity has to be able to flow in a cycle. And that's the same way with things like lightning. There has to be a break. The electricity has to flow from the sky to the ground and has to form a connection with the ground. Now this is called direct current because the current flows in one direction. Flows in one direction and it comes back to the source, the battery in this case, okay? Now, there's also something called AC current. By the way, DC current is things that you would use in your computers and is DC, and your car batteries are DC. Some of you say, well, don't we plug our computers into the wall? Yes, you do, but they are actually DC because if you look at your electrical cord, there's some sort of adapter there that allows it to convert from AC to DC. Sometimes that adapter is inside your computer. So DC stands for direct current. Current is kind of like the flow of a river, right? The direct current. The flow is going in one direction. AC stands for what we call alternating current. Edison was really big on direct current, and a guy named Tesla thought, oh, alternating current's going to be better because of some reasons and transmission lines and so forth. And so AC stands for alternating current. Well, in your house, on the wall, you have plug-ins there, okay? There are plug-ins in your wall on the house, okay? And these are AC current. You plug electrical in there, and this would be like 110 volts, 115 volts, something like that. And if you plug something into the wall, it comes out of one of these plugs, one of these connections, and it goes around and it comes back to a different one. There's a third button on there for grounding in case there happens to be an accident or a short in the system. Now, AC current actually flows differently. Let's put our light bulb over here again. Okay, here's our light bulb, and the current flows out of one of these, goes to the light bulb, and then it has to come back to the plug. But what happens is, in alternating current, for a very brief moment, it flows in one direction all the way around, and then it turns around and goes backwards the other way. So I have to turn all these arrows around, and they go backwards. The current goes back the other way. Now it's coming back this way. Okay, this is alternating current. The electricity flows going in a different direction, and the reason why that is so has something to do with the way in which motors work, and has something to do in the way in which we keep the thing stabilized and so forth. But electricity in your house is what we call alternating current. So sometimes, if we wanted to describe this current, we would describe it in a positive way, and then when it flows in the other direction, we would describe it as in the negative way. And it's for this reason that we need to be able to describe electrical current coming in the opposite direction as negative. So if you see a negative number in electrical current AC, you'll know that it's flowing in the other direction, negative square roots. So this is one of the reasons they do this. I don't know enough about all of the factors here, and I know that this is partly, it's a lot more complicated than this, but alternating current means it's flowing in both directions. We also use negative square roots in dealing with things like fractals and physics and going into outer space and things like that. So just a thing for you to know a little bit about why we use negative square roots. So the negative square root of 1 might work when the thing is flowing in the negative direction. There's other reasons for using this. Well, that's alternating current, and notice that most alternate houses are all alternating current, and cars and other things like flashlights and so forth are all direct current. Just a little information for you. All right, so just remember that tonight, as you're working through this, instead of using I, you're going to use J for electricity. And square root of a negative 1 is J. So J is now your new I when you're dealing with electricity. All right, let's take a look at your homework for tonight. All right, so here's that homework for tonight. A little more on the same section. You can't get enough practice on this stuff. If you're still puzzled about any of these things we've talked about, you've got to go back and take a look at the previous video, part 1. This was part 2 today. Here's your homework. We've already done like 12 through 17, almost all of those except for one of them, and then you've got some other problems to practice here. Go back and look at the other video if you need to remember how to rationalize the denominator. Remember, I and J, or J, cannot be in the denominator, so they are radicals and have to be moved by that process of conjugates. You have a test coming up. That's on May the 6th, 6:55, this chapter on radicals. Okay? On radicals. All right, enjoy this and have a good time with it. Don't miss the next video, because I'm going to go through a review of the entire chapter, doing one of the assignments with you. So I'll be doing the next assignment. That's assignment number 32. I'm going to do all of those problems and help prepare you for that test. All right, take care.